Integration by parts, level 2. Alright, we're going to dive in and work on various examples. Recall that integration by parts is particularly useful for integrands involving products of algebraic and transcendental functions, such as logarithms, exponential functions, and trigonometric functions. Let's try the first problem. Find the integral of x times e to the x dx. Alright, we first need to notice that the integrand contains a product of two functions, specifically x and e to the x. This is a perfect candidate to use integration by parts to find the integral. Let's use the first form of the integration by parts formula. Remember, the first step is to make a choice and determine which of the two functions will f of x equal and which one will g prime of x equal. This is a critical step when applying the integration by parts formula. Keep in mind that you want your f of x function to be a function whose derivative, f prime of x, becomes much simpler than the original f of x function. In the same manner, you want your g prime of x function to be relatively easy to integrate. Following these steps, we have that f of x will be represented by x, because when we take its derivative, we end up with a simpler function, specifically the constant 1. Likewise, we let g prime of x be equal to e to the x. Now we need to take the derivative of f of x, so the derivative of x is just equal to 1. Next, we need to integrate g prime of x to obtain our g of x. Integrating e to the x results in the same function e to the x. Now that we have our four functions, f of x, f prime of x, g of x, and g prime of x, we substitute them into the integration by parts formula, as follows. Finally, we take the integral of e to the x, which is equal to e to the x plus a constant. So the final answer is equal to x times e to the x minus e to the x plus c. Alright, now let's work on the same example, but this time, let's use the second form of the integration by parts formula. This is usually taught in a typical college-level calculus course. The first step is the same. We need to decide what function u will equal to and what function will dv equal to. Remember, you want u to be a function that becomes simpler when you take its derivative, and let dv be a function for which you can easily find its integral. With that said, we let u equal x, and we let dv equal e to the x dx. Make sure you include the differential dx when selecting your dv. This is an important detail. So now we take the derivative of u with respect to x and solve for the differential du. Doing that, we obtain that du is equal to dx. To obtain v, we take the integral of dv, or in this case, the integral of e to the x dx. Doing that, we get that v is equal to e to the x. Now that we have u, du, v, and dv, we substitute them into the integration by parts formula, as follows. Then we find the integral of e to the x, and doing that, we see that the final answer is equal to x times e to the x minus e to the x plus c. Alright, from this point on, I will use the second form of the integration by parts formula, specifically the u dv form, since it's the common formula that many college classes teach. Personally, I like using the first form, but you should use a form that is easier for you. At times, you might have to rewrite the functions in the integrand in order to apply the integration by parts formula, like in the following example. Find the integral of the natural log of x over x squared dx. Notice that we don't have a product of two functions. We actually have a quotient, but we can actually rewrite the function in the denominator by using a particular exponent rule. We can rewrite the rational function 1 over x squared as x raised to the power of negative 2. And now this integral can be rewritten as x to the negative 2 times the natural logarithm of x. Notice that we actually have a product of two functions. So now we can go ahead and apply the integration by parts technique to find the indefinite integral. So the first step is to assign a function for u and one for dv. Remember, we want u to be a function that becomes simpler when we differentiate it, and we want dv to be a function that can be readily integrated. If we assign u to be equal to x to the negative 2, and take the derivative, notice that we actually end up with a higher power rational function. Likewise, if we assign the natural log of x as our dv, we would have to take the integral of the natural logarithm, which at this point we have no idea how to find. So these particular choices of u and dv will not work. Let's reverse them and let u equal to the natural log of x and dv equal to x to the power of negative 2. Having assigned u, we take the derivative with respect to x, which is equal to 1 over x. Then we solve for the differential du and obtain 1 over x dx, or written another way as x to the negative 1 dx. Likewise, having assigned dv, we integrate it and obtain v, which is equal to negative x to the negative 1. Now that we have all the required functions, we substitute them into the integration by parts formula. Doing that, we have the following expression. The natural log of x times negative x to the negative 1 minus the integral of negative x to the negative 1 times x to the negative 1 dx. Simplifying the expressions, we obtain the following. And taking the integral of x to the negative 2, we obtain negative x to the negative 1 plus c. And finally, we simplify the expression and obtain the final integral of the natural log of x over x squared to be equal to negative the natural log of x over x minus 1 over x plus c. Okay, recall that we had no idea what the integral of the natural log of x was equal to. Well, that is about to change. We can actually use integration by parts to find the integral of this function. Let's try the following example. Find the integral of the natural log of x dx. Notice that we don't have a product of two functions. We only have one function, the natural log of x. But looks can be deceiving. We actually have two functions, the natural log of x and the constant function 1. So we assign u to be equal to the natural log of x and dv equal to 1 dx, or more simply as dx. So taking the derivative of u with respect to x and solving for du, we obtain 1 over x dx, or written another way as x to the negative 1 dx. And taking the integral of dv, we obtain v, which is equal to just x. Substituting these functions into the integration by parts formula, we obtain the following. And finally, taking the integral of dx, we obtain the final integral of the natural log of x to be equal to x times the natural log of x minus x plus c. This example illustrates that we can actually use integration by parts to find the integral of a single function. It's just a matter of spotting and creating a second function. In this case, it was the constant function 1 dx. Alright, in our next video we will find more complicated integrals that require you to repeatedly apply the integration by parts formula.